the impacts of air pollution to people's health, we know that there is some sort of dependency between the air pollution. Some of the components of the air pollution, the particulate matter, with some of the subscript, particulate matter 10 or 2.5. We want to evaluate that impact to people, connect that to people's life. And the density of that particular matter in the air probably will vary over the day or over the year if we observe for a long time period. So let's make an assumption that we can model that density as a random variable. But what about how do we evaluate the people's health? And if we can come up with some sort of numeric measure and to quantitatively describe, probably different people will react to the component differently, right? Depending on your, the current health, depending on your age, the gender, a lot of factors. So this is, I want to, using this as a story to connect the topic today, which is dependency. And dependency is everywhere in our life. But how do we measure that? How do we, and in the transportation engineer and planner context, and how do we use that to interpret some of the data in a more meaningful way? Okay, and before we jump to some of the details, I want to share with you a modeling philosophy. I guess some of you probably already heard about this because I remember there's somebody else who gave a seminar before. I'm not sure when was that, but it's on the long list of, if you check the website seminar, there somebody cited this. It's saying that essentially all models are wrong, but some are useful. And this guy, Georgia Box, is a statistician, and he's already retired from University of Wisconsin-Madison anyways. And why most of the models are wrong? And especially when we connect this to the transportation field. We always say that transportation system is a complex system. It's very hard to model it. So why it's complex? That's because there's a heavily human behavior, driver behavior involved, right? And with that, let's bury this modeling philosophy in mind and think about a more specific scenario in transportation. I believe some of you guys know, the speed density relationship, right? Know the green shield model. And on the left hand, this is just the demonstration purposes. This, the different categories of the speed density relation curve using either, a linear curve or an exponential curve, try to describe the empirical, scattered plot. And on the left-hand side is we call a deterministic model. The feature is if we give one input, so the horizontal axis is the density and the vertical axis is the speed. If we have one density on the horizontal axis, then we can uniquely get one speed value. But based on our experience that this is not quite true. This is simple enough, and we can track the system analytically, but it's not realistic enough to accurately model the system, right? On the right-hand side is also a demonstration. This is not empirical data, but it's still the speed density curve. Let's just use the green shield model as an example, and we generate some sort of random by adding, an additional term, random term. So this will give us that if we generate one density here, the speed is not a single speed anymore. It's a distribution, right? It's a distribution of speeds. So under each density, the driver's choice of speeds is actually also a random variable. It's not a single value, right? Considering the general driver population. So I want to use this as a starting point to start the topic of dependency. And I believe many of you guys may have experience, doing like Monte Carlo simulation, right? And we know the general procedure of Monte Carlo simulation is we have to start with sampling from a probabilistic distribution, right? And run the system 1,000, 10,000, or 100,000 times trying to analyze the input, the output using either the histogram or other descriptive statistics. And one question people always ignore is the distribution of the input. Is there a dependency between the variables? In either the transportation engineering context or planner context, there are a lot of problems involve many variables, right? And with the heavily human-involved system, and most of the variables are not deterministic. And what's the dependency? And is there a way that we can quantitatively measure that? So that's the topic of today. I was a little bit trying to jump into this, but I forgot to introduce myself. For those of you who do not know, my name is Haizhong, Wang. I just moved to Oregon State University a few months ago, and I'm very glad to be here today, to share with you guys some of the understanding. I have to say that by no means I'm not a statistician or a mathematician. I'm only interested in some of the technique which can help us to interpret the massive data, transportation data in a more meaningful way, and we can make out more information. That's the goal. I hope that you can take away some of the takeaway in that space, okay? And with this, let's start moving to modeling the dependency. And how do we measure that? How do we measure that? When we run some of the linear regression between two variables, and we used a sort of coefficient, right? It's the R square or coefficient. If the number is larger than 0.75, we feel comfortable. If it's relatively lower than that, we feel that the correlation between the two variables are not strong enough, right? And that's one way. But that coefficient only can characterize the linear, we call the linear dependency. But most of the dependency structure between the random variables are not linear. So that's the motivation. How can we describe the dependency between random variables better than the linear case? Okay, and some of the if you look at the probabilistic probability literature, there will be two. Concordance and discordance, which means that if the two random variables, the larger values are correlated with the larger values with another random variable, the lower values are correlated with the lower values, it's called concordance. Otherwise, it's discordance. And that's another way to measure that. And measure the dependency in a more quantitative text. There's others. It's called a two-standard measure is called Kendall's law and Spearman's rule. You don't have to remember just know something is there and who can do a better job. And but this one is quantifying the random dependency between the random variables is still not complete. With that, I want to connect with that measure to in the transportation engineering or planner context. And in most of our case, the dependency, we can categorize into two categories. Either it's spatially dependent, or it's temporal dependent. For example, the spatial dependence, you think about the weather forecast and with the rainfall. This is actually, Copula has been applied to the civil engineering context in very successful in hydrology. So if you ask people who work in that area, they use that as a standard tool to predict the rainfall and the spatial coverage and the variability of the rainfall to the weather, to climate change. in the larger scale. And so the question we have here is that since most of the cases are spatial dependency, and is there a possibility we can capture the whole dependent structure without too much disturbance from the marginal distribution? Let's use a bivariate case as an example. Let's use a bivariate case example. And the answer is copular is an alternative option. And literally, the copular is a Latin word. It means that it's a link. It can tie something together. If we use the bivariate case as it can tie two random variables and like sort of give an umbrella to cover the two. That's the bivariate case. If it's more than that, 3 random variables or 4, it's a 3-dimensional, 4-dimensional. Right now, in the the hydrology space, people even use that in a higher dimension. But in a higher dimension, numerically, it will be more challenging to calculate, to numerically calculate. Okay, a standard material reference is called An Introduction to Copula, and the author is Roger Nielsen. Probably most of the guys don't know, but he is affiliated with PSU, Portland State University, and he works at a university called Clark College. I believe it's a private college in the city, and he is adjunct faculty at PSU. But right now he's already retired. Anyways, we'll spend some time to dig what is the copular and how can we apply that in the engineering context or the planning context. Okay, so some of the preliminary statistics, and the first 2 came from this reference from Thomas. That's the handout I have. I only have 15 copies, so I did not know there are so many people in the seminar. Anyways, the first 2 come from this reference, and the third one I did it. So if you put the copular in Google, and like in about 10 years ago, you get 10,000 results, and about 7 years ago, it's 650. You can sort of track the jump between just the number, and right now, if you put, it's about this giant number, and we can see that the popularity of the concept is, applying in different fields are just rocket speed, okay? And it is actually being used in very successful in financial area, in economics context to calculate the value at risk, which can connect it to the engineering context more in a risk modeling and management framework, okay? And a few background. The copular first discovered by this guy called Hoofding. And he discovered this in 1940-41. But originally, the paper was written in German, and it was in the Second World War. And nobody really, paid a lot of attention to that. And it wasn't, translated to English until 1960s. And the revolutionary work was done by a guy called Sklar in 1959. So right now, if you look at a paper related with this topic, you will see this theory called Sklar theorem. And this guy lays the foundation of the copular and connected the theoretical aspects to the application with that. And it was introduced in financial area only over 10 years ago, not very long, but it has been used as a standard tool in the financial area to evaluate the risk and returns, asset returns. And a couple of other areas, we'll skip that and take a look at this, the theorem. What does it say? Let's just try not too much to understand the details, but still use a bivariate case. Let's just limit this D as 2. So x1 and x2 are 2 random variables. And the copular is actually, you can think of that as a distribution function. Distribution function which can capture the marginal distribution of each of the random variable. This is F1 is the marginal distribution. If the two random variables are totally independent, then we know, the probability of random variable A and random variable depend is equal to the probability of one multiply the other, right? If it's independent. But if it's dependent, it won't be the case. We know that from the elementary probabilistic context. And if you look at this, it's confused by this one. It's actually a unit square. If we put it as a D as 2, it's 0 to 1 multiply 0 to 1. And the handout, actually, the guy who proposed that, why are we converting the random variable to a unit square? And right now, in literature, people are talking about, copular is so effective in terms of capturing the dependency between random variables. And why is that? It's called the flexibility, and because it's skew-free. And the skew-free comes from converting the random variable, the distribution, into a 0-1 space. Which means if we have, for example, if we have a random variable and it's 1, 3, or some sort of number, and when we calculate, we first convert that into a 0-1, but actually is the probability, is the probability, okay? So right now you can get to the point that copular is a distribution function, and that's it. And it can capture the dependence between the random variables, and we'll show that using an example later on, okay? Some of the application, like I said, we're interested in application. We're not doing research in the statistical context. We're only interested in how can the tool can help us interpret the data in a more meaningful way. And in civil engineering, a group in University of Colorado, Denver applied this in a bridge reliability study. And the paper has been published by Transportation Research Board, Research Record. And like I mentioned, the climate and the hydrology context, because most of the hydrology events are multidimensional. Actually, not just the hydrology. In transportation, the same. Most of the events are multidimensional. For example, some of the extreme events, the happening of a tsunami, the happening of earthquake somewhere, it's not totally independent. It's somehow dependent, but the people don't know the dependence structure because the unavailability of those data in a relatively long observation time period, okay? And a couple of other area that you can, just that it's widely applied. I won't, iterate that one by one. And let's look at how the transportation engineers and planners are applying this context. I believe some of you who are working in this space knows the name of probably this guy, right, at UT Austin. And his group started applying this copular to the choice modeling, to modeling people's choice behavior, the travel behavior, in a relatively recent, like 4 or 5 years. If you track, the publication records, it started in 2008. The first time I saw copular over TRB annual meeting was in 2009. A guy from Princeton, he applied this to the routing decision on the network, because use the travel time as a random variable. Like the travel time in the network on each link is a random variable, and how the dependency of the travel time affects the people's routing behavior in a network, and evaluate, probably the congestion effects in the larger scale. That's the first time that I saw that in 2009. And if we summarize this group's study, is what the group did was, in the utility, like for example, some of the different modes of transportation, each one, you have a utility function, right? Utility function, at the end of the utility function, there is a random variable taking care of all other variables that we did not model in the equation, okay? And what they did was just to manipulate that random variable and generate tons of publications in different space. But we're more, interested in how this can apply in general in the transportation engineering context. If you look at others, there's like modeling the injury severity of to the safety area, also to the safety area. Regarding, I did not put a single equation, regarding the different type of copula. Like for example, the Gaussian copula or student T. Don't be scared by that. Some of the package, for example, MATLAB or R, those type of statistical or numerical package already implement that. We just know that, or we just call that a function in MATLAB. Or R has a package called Copula. If you put the R Copula in Google, you will get that. And it has a lot of examples regarding how to apply that in different scenarios. So with that, let's move on. Here, the behavior modeling. Like I mentioned, the choice behavior, the mode choice, and the number. This one is the number of stops. It's more in the planning context. You can see that this publication is pretty recent in the past 2-3 years. This is how, if you're interested, you can just go check each of the publication. It's the PDF or the Word file is on his website. Okay, you can check that each paper. I won't spend more time on that. Another, like I mentioned, is the hydrology. Hydrology people use that as the standard tool to, for example, modeling the oversaturation risk. Some of the, like for a city area, when the rainfall process is very heavy, what is the overspill risk of some of the pipelines underground, and how that will, like if we can connect that to transportation or safety, is how that will affect the pedestrian or bicycle, safety in that extreme events. Not the drizzles, this heavy rain, okay? And that's something it has been studied. Another takeaway probably from here is the uncertainty, and we call the random variable. There's uncertainty involved. There's a lot of people using stochastic process to describe that, to trying to understand how uncertainty is modeled or propagate in the model, at least. Okay, but I personally feel that a stochastic process is much harder to take care than Copula. You probably can understand Copula in 5 or 10 minutes, but I guess to have a much better understanding of a stochastic process, it can take years, 5 years. So you can sort of evaluate if you want to generate some papers, and this is not a bad starting point. I'm not sure how DOT people like that idea, but it's a very good topic applying for the transportation and engineering content for a master thesis or a dissertation. There's a lot of research on that. But regarding integration of the Copula and stochastic process, right now is heavily studied subject in probability. It's technically more challenging, but like I said, we are not doing research in that. We're only interested in the application, and what does that mean to our scenario, to our engineering field, okay? And there's another paper on the uncertainty part, okay? So if we have, let's remove one LaTeX typo. If we have a certain scenario and we need a Copula model to estimate parameters, like I said, MATLAB already had built-in functions using Gaussian Copula and Clayton, or different type of, each one has each formulas, but I just skipped that if you're interested, you can certainly dig out. Almost every standard reference contains that information. Okay. Two simple process to develop a model is we start with a marginal distribution, right? Still use the elementary bivariate case. For each variable, we can know the marginal distribution, and the copular is tying the two marginal distribution together with another additional parameter. In MATLAB, it's called rho. It's just the estimate. Using the estimation method is actually maximum likelihood. It's very standard. To estimate that, and then we can estimate a copular function. And copular function also has the predictive power. It's modeled that system and can predict the behavior in the future. Okay? And simulation-wise, also, MATLAB and R can take care of that. It's just two general procedure. Draw samples, like the Monte Carlo simulation idea. It's about exactly the same to calculate that the risk. Okay, so here's a Gaussian copula, like I mentioned, bivariate case, and it has been converted to the unit square. The unit square means the 0, 1 times 0, 1, right? If D is 2. And let's take a look at, this is the correlation that I mentioned. The correlation rho is when the correlation is 0.9 is larger, it's a numerical value between -1 to 1. It can be a negative number. A positive number means the positive correlation between the random variables is this diagonal, positive diagonal. When the plots are densely compacted on the diagonal, it means a stronger dependence between the two random variables. So if you want to identify whether there is a dependency between the random variables, you can use that to check. And starting from the empirical observation and fit to a copular, if it's widespread, like the points are equally spread in the unit square, then it means that if not no, at least a very low dependency between the two random variables. So you can see when the number change from larger to small and from positive to negative, how it varies. And most of the paper, if you read paper in this space, most of the paper is about using Gaussian copula or student T copula because it's analytically tractable. It's analytically tractable. Thank you. So student T. Student T involved two parameters than the Gaussian copula, and with the varied correlation and this is called a freedom, degree of freedom of the parameter, and with the same implications. Okay, so let's use one example in the transportation engineering context. This is actually two corridors from Georgia, called Georgia 400. There are 100 observation stations it's actually collected by video, and it's use the sort of the virtual loop, to distract those data. And what the problem here is that there are 100 stations, but 78 are on the basic freeway segment, and 22 are on-ramp and off-ramp. So 11 entrance ramp, 11 off-ramp, or the exit ramp. So the problem I was investigating here is that I assume that the flow in peak hour in the morning, like from 7 or 6 to 9, in the afternoon peak hour from, let's say, 5 to 7 or 8, okay? I assume that the number of vehicles past that on-ramp only invest the on-ramp, because the on-ramp is, the number of vehicles getting on the freeway is most sensitive to the congestion effects on the basic freeway segment, right? Because cars, you have to use either one on ramp to get on the highway, right? So the problem is, what's the dependency between those, if we assume that each of them, the flow are random variables, and what are the dependency? And is there a dependency? Okay, so I only investigate the two off-ramps, the northbound, and the two on-ramps, southbound. This is the direction of entering the city of Atlanta, the Georgia 400. There's actually a circling road, which is 285, I guess, is one of the most, the busiest road in the country, like top 5, something like that. So let's take a look at a flow pattern on one ramp. This is the number of observations. It's not the time, so we can see starting from midnight to over the whole day. We can start peak, morning peak, and afternoon. This type of pattern. If we feed a distribution to the flow pattern over the whole day, we found that it's not normal. It's not normal distribution, right? And when it's not normal distribution, we cannot formulate the problem as like a multimodal normal distribution. Because if it's jointly normal distributed, we don't need Copula. Because mean, we can calculate the mean, we can calculate the covariance between the variables. That will explain the whole story. We don't need Copula. Copula only applies when the distribution are not normal, is heavily tailed, is screwed. It's not a normal distribution. So then let's take a look at the correlation between the on-ramp and off-ramps. So with the detector start with the 4005. This is the different ID. And we can see the diagonal is 01 because it's actually dependency between that one to itself, right? And you can see the number varies. Some are higher, some are lower, some are positive, some are negative. That's expected, okay? So this is the morning peak hour. And we won't spend time on each of the number, but this is the afternoon peak hour, the dependency between the ramp flows. With that, and we are able to ask those the parameters that we estimate from the empirical data, and we formulate that as as if it's 10 ramps, that's a 10-dimensional Copula. But in MATLAB, we can estimate higher structure, higher dimensions. But when we plot, we cannot plot a 10-dimensional joint distribution function. So we can only plot 2. So what I did was I paired them up with just using the geographic difference. It's because every ramp it's about certain distance between the two ramps. We probably expect when the ramp are geographically distant, longer distance, the dependency will be lower, right? For example, the people's routing behavior in the regional behavior in the morning peak hour, in the afternoon peak hour, and also on the off-ramp, on the on-ramp, the dependency probably be negative. It's not positive, as you can see from the correlation matrix. And so what does this tell us? What does this tell us? It's basically means that some lines on the unit square. It actually means we can convert the unit square back to the numerical value. For example, the flow is 400 in that hour or 600 in that hour after we estimate the parameter and using some sort of technique also. Like I said, it's already implemented in MATLAB. Don't worry about that. Okay? And it's the joint probability. It's joint probability. So if we know that the flow pattern on one and flow pattern on the other one, all the flow patterns, then we can, one application probably, to figure out the ramp metering strategy, right? How do we manipulate the flows entering to the highway on the ramps to control that, to make the flow on the freeway, basic freeway line, the main line smoother, right? reduce the overspill risk. That's one, I would say, the big potential of applications. Okay, and that's we are using a we call it parametric, because like I mentioned, the Gaussian student T with parameters. If we use a non-parametric, just feeding that empirical data, we don't even know what type of distribution the marginal distribution is. We just use non-parametric method to do the same thing, to plot the dependency structure. And it's hard to visualize the difference, but if you look at them more, you can still see the difference between the structure. Some are higher, some are lower, and with a different numeric value. This is on the day, the morning peak on this day. And this is another day. It's another day in the same month, right after the new year in 2003. The data is a little bit old. You can see that if we compare this, match this back to the big map we just looked at, the dependency between 0, 4, 0, 0, 5, 0, 1, and 0, 2 are the ones which actually far away from the 285. This one is the one which is closer to the 285. And you can see the difference, right? I see the difference of the dependency structure between the ramp, which closer to the 285 and further away. Further away, it means like about 50 miles. 50 miles because the corridor is about 20 miles long, 20 miles long corridor. This is using a Gaussian Copula. This is using a student T. But actually, you did not see a big difference between the two, because the student T and the Gaussian Copula is actually when the parameter rho, the degree of freedom, when it's a relatively larger number. Approximately, the student T distribution will approximate the Gaussian distribution. So that's why when you see the plots here, you did not see a drastic difference between the two. Because these two are the simplest. So that's why I use this as an example, which doesn't mean that others are not applicable to this context. Okay? So to another, this is the two-dimensional student T applying for the afternoon peak hour. Like afternoon peak hour, I model the exiting the city, because in the afternoon peak hour, the exiting the city, the traffic is dominating, right? In the morning peak hour, the traffic entering the city is dominating. So that has been differentiated. And using a simulation to transfer the unit square back, like I said, it's already implemented. We don't have to do a lot of things, just call the function and convert it back, and we can figure out the marginal distribution of the ramp flow, and also the dependence between the two. And these two, we can see that it's quite scattered. It's not really densely populated on the diagonal, which means the dependency between the two is lower rather than higher, right? I mentioned a couple of times. So MATLAB has built-in functions, and R has the Copula package. You can apply that. You don't have to do a lot of programming to make that happen, just a few lines. A few takeaways here. I actually referenced to this guy, Daniel Berger, as he did a presentation earlier. He summarized some of the features of Copula, and I gave him the credit here. And this is some of the takeaway that you might, we won't go through them one by one. But if you do not remember anything from the presentation, I hope that you can take away at least one, which is Copula, when you, in a context of trying to figure out the dependency between multiple variables, when you feel that, oh, the coefficient is not enough, then try this. And it's not a guarantee that it will work in every scenario, but at least it's an alternative, right? And with that, I will conclude the presentation. This is my friend. I had constant conversation with him regarding the Copula stuff over the past few years. So I really enjoyed that. Thank you, guys. I hope that I did not make you feel so boring. Okay. So, any questions? Hopefully, answers. Yes. My name is Michelle Yuan, and I just wanted to ask, do you know if this method is used to model water distribution? Water distribution system, like the one I mentioned, is the hydrology context.
Hydrology, okay.
Trying to calculate the overspill risk in the certain, larger net. We're talking about the transportation network hydrology. They are talking about the pipeline, under the ground, the overspill risk. That's in the literature. It has that.
Okay.
Yeah.
Okay. Thank you.
Yes. Thank you. Yes.
I spend a lot of time in Atlanta every year, and I have a lot of relatives there. And I have driven a lot on 285, so I was really curious, what exactly are they trying to do by figuring out the correlation between, some of these on and off ramps?
That's a good question. It's a tough one. My understanding is that, when we develop stochastic models, trying to accurately model a system, trying to incorporate random events or because random are happening on daily basis, right? And in that case, if we do not have a specific assumption or specific structure of the dependency between the structures, it's very hard to develop a meaningful stochastic model. That I would not give that to the credit to mine. It's actually an argument from a paper. I'm not sure whether I put it over here. Is when we develop stochastic models, we have to figure out, like doing Monte Carlo simulation. And you can just ignore that, but how the results are, to what extent it's true, it's a question mark. I hope that I can answer that question, but I'm not sure.
Okay.
Yeah. It's without assumption of the without knowing the dependence or assumption of the dependent structure, the development of the stochastic model is challenging, or is the model we cannot ensure the quality of the stochastic model. Yes.
Thanks. Can you explain a little bit more how this interfaces with regression modeling? Because in specific, I'm kind of wondering, is it used more to generate like error correlation matrices, or are we looking at, say, a group of observed potentially explanatory variables, and we're trying to better quantify the association between observed variables, if that makes sense?
Yes, that makes sense. My understanding is that this gave us a quantitative way of measuring the dependence. We used to know like something is dependent on something. We know it, or we assume that it's there. It exists, by some common sense or by experience. But we do not know quantitatively. Regarding, whether the Copula can give us an answer like accurately, I wouldn't say it can give an accurate, a real the number which is accurate or perfect number. But it's one way. It's a quantitative way to measure that dependent structure, especially when we do the simulations, like trying to calculate the risk, overspill risk. Without that, in the quantitative structure, we're not able to do that. We cannot calculate the overspill risk. For example, on the freeway main line, and when what is the random flow on the ramp, how it varies on that jointly. not just one entrance ramp, that will affect the mainline traffic, and every segment has a capacity, right? When it's exceeded the capacity, then it will break down. Speed will drop. That's my understanding. Yes, go ahead.
I just to clarify a little bit of the use of the concept in general, you keep using a phrase that I really like, dependent structure, and it seems like one of the main advantages of this method is that you can create a large map using fairly disparate data because it kind of comes back down into a normalized distribution. So,
right.
And the main idea is that once you have that, you have an actual quantitative map, even if it is in 10 dimensions, but data-wise you can use that. So so that is the main kind of advantage here.
That's the attractive That's the attractive feature of Copula. And a lot of people, we don't know that, but it's popularly accepted and widely used in the risk modeling management and calculating the in the financial area, calculating the value. They call it value at risk. VAK. If you look at the that literature, it's the common word.
Excellent.
Yeah.
So you mentioned the Monte Carlo method. What is that exactly?
It's basically is there a complex system, and we do not know the system behavior, right? If we just run, for example, we run the system, we have a model, right? We have a model to describe that system. We want to know that how this model, performs in terms of describing the complex system, right? If we just run the model one time, okay, it's matched the system. We'll claim, this is really a good model because it matched the that empirical behavior. But one time is not enough, right? We have to run the model, run the same model 1,000 times, 10,000 times, from a longer time horizon to look at the statistical behavior. In the long run, if it can generate, for example, 95 confidence interval, in the 95 confidence interval, then we can claim that, it's reliable rather than just one. Does that make sense?
Yeah. Thank you.
Yes. One more question? Yes. Hey, Roger.
Hey. So just a slightly technical one, but so when you apply the Copula method, right, do we need to know anything about the marginal distribution, or can it be something non-parametric? So what you showed there was, you said you had some distribution, you said it wasn't normal, but the
marginal distribution, that's another attractive feature. The two random variable doesn't have to be continuous for both of them. It can be one continuous and one discrete. That's fine. That's why this is a tool that people like this so much. I'm not sure how practical. Let's put it this way: be straightforward, be honest. I'm not sure how practical it is, but in terms of generating a quantitative structure between random variables, right now, based on my literature review, I do not know a better way than this one. Let's put it that way. Okay, probably there's one, but I do not know.
I think that depends on the context, right?
Yes, for the marginal distribution, we can either figure out, from the empirical data. Yeah. From the empirical data, we can, or if we do not have empirical data, assume a distribution based on experience or intuitive understanding. How's that?
Yeah, that's fine.
Any others?
Thank you, Haizhong.
Yes.
I have a question that maybe you can try to link this to more kind of traditional statistics. sometimes when you try to estimate a parameter, you want to have a method that is consistent, unbiased, and asymptotically, well behaved. And so I'm just trying to, maybe you can comment on how this method relates to all these statistical concepts. Like, we learned that are very important and very well established in the literature.
This is a very challenging question for me. I'm not sure I can answer that, to be honest. Right now, following what I showed here, I'm working on a Bluetooth. Chris knows that David Porter and David Kim, they applied some of the Bluetooth device on the 99 West and collected some travel time data, which actually is about 5% or 10% of the general traveling public on the arterial with 4 signalized intersections. So the signalized intersection is about 1 mile between the 2 intersections. So they have the Bluetooth device read the data. If you have your cell phone and it's on, you don't know, they will read your MAC address, but don't worry about that. They don't know who you are. So the travel time, know the travel time in each of the 4 segments. I'll come back how it's related to that context. The goal of the project from ODOT was trying to identify, using the travel time to identify the incident. For example, we know the distance between the 2 intersections, and we know the speed limit, 35, 40, right? We know the travel time on average. If there's something happens, for example, an accident or some other sort of events, the travel time may be, peak to a certain large number, right? If that's the case, if we don't know exactly what's happening, but we know something is happening, right? But I was trying to use that idea as, if we only know, because it's a signalized intersection, right? Probably it depends on the congestion or even the signal timing stuff. If we only know one segment, the travel time is larger. Probably it's not enough to conclude that, there's something happening. If we jointly model the different segments, the travel time, are the joint probabilities is higher. It's just an idea. It probably can give us a better idea regarding what's happening. You know what I mean? So just one segment is not enough. Figure out the marginal distribution of the travel time and then another distribution time using the bivariate copula to model that, or use the 4-dimensional because the 4 segments. And we come back to the statistical study. Right now, I'm calculating the overspill risk. And to be honest, I'm not sure. Right now, I can generate the curve, regarding when the random flow change on the different entrance ramp. It varies on different entrance ramp. I can calculate the overspill risk on the highway. Right now, I do not know how to validate that. Why this is true? Why should I trust that curve? Another way is just running that change the random flow pattern on the entrance ramp. Run Monte Carlo simulation. Right now, I said 10,000 times, and analyze its statistical behavior. It's not just the one time, and use that, to calculate, to fit to a 95% confidence interval. Use that type of method to support that it's a relatively reliable method. Hopefully, I answered the question to some extent. This is a very, a different topic I would like to, share with what I understand in the past few years, and hopefully can provoke or stimulate some of the thinking. And in the future, when you are working on modeling stuff, or some of the problem happens to be in this, you have to figure out the dependency. You probably, just to refer back and try it, right? At least probably you'll generate the paper. How's that?
So thank you, Haizhong. I'm sure you got us all thinking, so You did a good job.
Thank you for inviting me.
Thank you.
Okay, thank you, guys.